Okay, we still need to finish one of these in section 4.7, and then we'll move on to section 4.8 and do a few of those today. So I'm on E here, and E says let f of x equal x to the fourth minus 2x. Let the graph of G have a vertical stretch of 2, followed by a translation 3 units up. And you saw some of these on your homework. I helped a few of you, but it's easier if I just teach you what this actually means instead of individually. But so a vertical stretch of 2 does what it's always done. Okay, it takes your graph here, x to the fourth minus 2x squared. Okay, and if it's a vertical stretch of 2, everything has to be stretched by 2. Okay, so if you distribute that, that's 2x to the fourth minus 4x squared. Okay, that's what a vertical stretch looks like on this polynomial. Let me back up because I don't think that I was clear in why this one might be different. Do you see here, I'll zoom the camera in, do you see here how this polynomial here is more in standard form, whereas these are in what we call vertex form? Okay, now you could go through and put some of these in vertex form. I highly recommend you don't do that. Okay, that you would have to complete the square. Heaven knows you don't remember what that is. So just recognize that when you see two x's here, you got like an x to the fourth and an x squared, that it's going to take this process. Instead of the left one down 4, that stuff still holds. It just looks a little bit different for us. Okay, so this is a vertical stretch of 2. And now we need to go 3 units up. Well, 3 units up, just put a plus 3 on the end, so that's the same thing that happens here. So that's your final answer for E right there. Okay. F requires a little bit more work. All right, it says let f of x equal x squared plus 2x plus 1. Let G be a reflection over the x-axis, followed by a translation 1 unit left and 4 units down. Okay, so you start with your polynomial, x squared plus 2x plus 1. A reflection in the x-axis takes everything and flips it. So that's the same thing that's going to happen here. We've got a negative x squared minus 2x minus 1. And then, so that's the reflection. So we're good there. Let G be a reflection over the x-axis. Done. Followed by a translation, 1 unit left. Okay, here's how things go different for us. Okay, when you usually went left, it looked like this, right? You had an x plus 1 in the middle, or in the inside. And we're still going to do that, but now we have 2 x's, right? And so we're going to have to put that x plus 1 in both spots. So we've got a negative, and then x plus 1 squared minus 2 times, you have to put the left right there as well. Okay, and then you keep that minus 1 on the end the same. All right, and now let's clean this up just a little bit, okay, because we can. Sometimes big ideas will accept it if you don't simplify it, but I would prefer that you did. You can keep that, okay, you don't need to write that out twice in FOIL. You can if you wish. You do not have to, okay. But you can distribute that too. That is easy. If it looks easy to simplify, go ahead and simplify, okay? So you got a minus 2x minus 2, and then you still got this minus 1 on the end here. And so then we can clean it up a little bit further to be negative x plus 1 squared minus 2x minus 3, okay? So that takes care of the 1 unit left. And then the easy part, we got to go 4 units down. So that means we just got to subtract 4 more, okay? So then if we finish cleaning this up, you end up with a negative quantity x plus 1 squared minus 2x minus 7. And that's where you can stop. Okay. So moral of the story with this one is all the same rules apply. You just have to remember that they apply to all the x values. So if there's, 3, if it would have been like x to the fourth, x cubed, x squared, you have to put that translation left and right in every single x spot. Okay. If you have questions about that one, there's 2. I think there's 2 questions about that on your homework, maybe 3. Follow these, see if these notes help, and then send me a message on Remind, and I can help you there as well. Okay. All right. let's get into a little bit of 4.8. I will finish 4.8 on Monday, but I want to get you at least started on it so that we're not crammed for our tests next week. So 4.8, we're going to do some more graphing. And again, you're going to have the graphing calculator for this, okay? So this is a very, very powerful tool. And so I want to make sure that we've gotten a really good idea of how to use it properly. So the first part says, tell how many solutions each polynomial has. Then identify how many are real and how many are non-real. So we used Descartes' rule of signs 3 days ago, to determine all the possible, positive, negative, and real zeros. And I lost a lot of you. You looked glazed over, okay? The cool thing is you can use the graphing calculator to definitively tell you how many positive, negative, and real zeros each have. But the question is only asking here how many are real and how many are non-real. Okay, so all we got to do, we go to y equals, okay, plug in this polynomial. 2x to the third plus 6x minus 4. Okay. And then you go to the graph. If your graph doesn't look centered like mine does, okay, if you hit this zoom button and then 6, that'll bring you back to your square. Okay. I think that's a thing that I think most of you have probably figured out by now, but if not, it's very useful. Okay. And so remember, zeros are where this graph crosses the x-axis. Okay. And we're going to assume that we can see all of them on here, which means that it doesn't come back like over here awkwardly where you can't see it and come back down again. If there are zeros on the graph, you're going to be able to see them within the first 10 units. Okay, I'm not going to hide it somewhere far off and gone where you can't find it. But this graph only crosses once. Okay, so that means that you have one real solution, but you know from the fundamental theorem of algebra that it has to have 3 zeros total. So that means that 2 are imaginary. Okay? Because it has 3 total. Okay? So here, you know that you have 4 total. So let's graph this and see what it looks like. All right, so this one looks a little bit like a parabola, not quite, but as you can see, it crosses twice, and there's no bounce. Keep in mind that bounces count as 2, so that might pop up, okay? But these don't bounce, they just cross twice. So that means that you have 2 real, and then you have 2 imaginary, okay? Same thing on C here. Go to y equals, clear that out. 2x to the 4th plus 4x squared plus 3x plus 1. Put that into y equals there, and then hit that graph button. Oh, man. All right, well, I don't know. You could probably see it on your calculator. I'm going to zoom in just a little bit just so you can see it a little bit better. But as you can tell, this, what looks like a parabola but is not, right? We've talked about that, is not ever touching the x-axis. And so when you have a polynomial that never touches the x-axis, and I'm asking you to find the zeros, okay, none of them are real, right? It's never going to cross. So you would say 0 real, but you know that there are 4 total, so that means that 4 must be imaginary. Okay? And it's always just good to know this because we're going to start graphing again here in a second, a little bit more detailed than the last time that we graphed. And it's good to know this stuff so that you know that you have all the parts. Okay? This next section here is called the location principle. All it means is that if you have a graph that has a point down here in the negative y range and a point up here in the positive y range, that it's going to cross the x-axis at some point. That's all the location principle means, okay? It's very helpful in calculus and in some other math classes, but they just mention it here so that you're familiar with the idea that You know, if you have a point down here in the negative area and you have a point up here in the positive area, it must have crossed the x-axis at some point. That is all that it's telling you. Okay, so don't overthink that too much. Alrighty. All right, so now let's talk about some more key aspects of a graph. Turning points and increasing and decreasing intervals. You should have talked a little bit about this in Algebra 1 with quadratics, but just in case you didn't, we'll go through it again. So turning points are also known as, we call them local maximums and local minimums. And you dealt with, you know, we've talked about the minimum and the maximum of a parabola before, right? It's just the highest or the lowest point. Well, now, what if you have a graph that looks like this, right? You have two minimums and then a maximum. But if you had a graph that goes like this, you have two of each, right? Well, really three minimums and two maximums, okay? So that's why we call them local, because there's probably going to be more than one. And if there's not, well, then you can just call it a maximum. That's fine, okay? So the actual definition here of a local maximum is a point that is higher, and I'm going to put it in quotation marks because that's relative to what's around it, okay? And we're going to say that, a point that is higher than the points around it. Okay, and similarly, a local minimum is a point that is lower, I'll put that in quotation marks, lower than the points around it. Okay? That's just, you know, definitions of the pictures that I just drew, basically. You might even be able to draw, like, you know, arrows. Those are local minimums. That's a local maximum. Pictures help you guys, you know. Great. Okay. And these turning points, these local maximums and minimums, okay, they're very helpful in calculus. So if you're planning on going to calculus, just keep this in mind. They help us determine the intervals for which the function is increasing and decreasing. And that just means where we're moving up and where we're going down. So like here we're decreasing, and then after that turning point we start to increase, right? And then we start to decrease again, and then we start to increase again. We'll talk about that when we see an actual graph here. Okay. All right, beautiful. Okay, really only one core concept, because I'm not going to talk much about even and odd functions. If you would like to know more about even and odd functions, come talk to me. I'll talk to you about them, but they are not in our curriculum anymore. I don't even think they're a state standard anymore, so I'm not going to talk about them, but know that there's other things about graphs than what I'm teaching you. If you have a question about it, let me know. But this is just a really useful information for us. Turning points. So what this means is that if you have something like x to the third plus 2x squared plus 3x plus 1, I don't know, I just made that up, okay? You will have at most, this is like your degree, that's what we called n, right? You're going to have at most n minus 1 turning points. So what that means is a cubic function is going to have at most 2 turning points, okay? So what that means is that you might turn around only twice. At most twice. You might only turn around once, right? Because sometimes if things are imaginary, if you have imaginary zeros, then that's going to throw some things off, okay? It's just good information to have. I'm not going to look at you and ask you, you know, oh, what's the turning point of a polynomial function theorem? I'm not going to do that to you, okay? Just good information to have, all right? So now let's take all this information that we got and let's graph it. So whenever you see the word graph each function, your first instinct should be to go to this calculator, clear it out, okay, and plug in the polynomial that's there. So we've got a 1/6 times x plus 3 times x minus 2 squared, okay? And just so we know ahead of time, we're looking for 1, 2, 3 zeros. I just like to know kind of ahead of time. That's kind of where we're going with this, okay? And then we go to our graph, and my calculator is still set on the setting it was last time. So I'm going to go back to Zoom 6 here. All right. And that's what my polynomial function is going to look like. So now I'm going to graph it on here. So I go to my table. All right. And looks like the first one I can plot is -4, -6. Then -3, 0. Then -1, 3. 0, 2. 2, 0. 3, 1. And I'm going to keep going until I can't plot anything else. 5, 12. You could go over here, and if you wanted to go off your graph, you could. But that gives you, and you can always go back to your picture, too. Go back to your picture and say, oh, okay, so I can connect the dots. So then, as best as I can, I connect these dots here so that it looks like a cubic function. We talked about a lot of cubic functions are going to look like S's, just in different ways. Okay? So there's your function. Now let's fill in the information that we have here, the zeros. Well, just look where this graph crosses the axis, okay? You've got a 0 here at -3, and then you've got a 0 here at 2. But what you do need to do is tell me why this should have 3 zeros, why you only see 2 of them. And there could be 2 different reasons. One, because one of them is imaginary, or because there's a bounce. And in this case, you've got a bounce. Okay, so it's just good to know. So if I ask for it, you might need to tell me that. All right. Then we've got a y-intercept here. Well, the y-intercept is where it crosses the y-axis, and that's at 0, 2. Okay. End behavior. Just draw the arrows. The first arrow goes down. The second arrow goes up. Right? You could have used what you know about end behavior from a couple sections ago, but my guess is you don't remember that. And that's okay. You have a graphing calculator. All right, now this maximum, you are going to have to use your calculator here in order to do that. And so we're going to do it the same way we did with parabolas. You hit second, trace, and then you go to maximum there. Okay? So if you click maximum, and then it's asking you for the left bound, click enter, and then go over, click the right bound, click enter, and then you're left with the maximum of -1.3 repeating, so you can just round, -1.3, comma, 3.09. Alrighty? And then you do the same thing for the minimum, except you don't really have to because you can already tell on this graph that minimum there is going to be 2, 0. If you wanted to do the minimum, you could. You could do second, trace. You could go down to minimum, right, and do left bound, right bound, enter, enter, enter. Right, so if we did that, you would do left bound, right bound, enter, enter, enter. And you get the minimum of 2, 0. Okay, that's fine. Increasing and decreasing, though, we do need to take a second to talk about increasing and decreasing intervals. So you're increasing when you're going up. Okay, so let's just start down here. You're traveling along this parabola, so that means you're going up, and you're going up until x is equal to -1. Increasing and decreasing interval are talking about x values. What x values are you increasing? What x values are you decreasing? Okay, so from here, all right, we're going up. So you're increasing until x is -1. So you're increasing when x is less than, or yeah, -1. You don't put equal to, okay? You're increasing when x is less than 1. And then you're increasing again over here, right? And the x value that occurs at is 2. So you're increasing when x is greater than 2. Okay? And then you're decreasing here. You're decreasing in between those two values right there, right? That's where you're going downward. So you're decreasing when x is in between -1 and 2. Right? It's actually not, sorry, it's not negative, it's -1.3. I apologize. It's this maximum value, which is what you found there, -1.3. Sorry. Forgot to label it. Normally I label it on my graph and I forgot this time. Okay. Okay. As long as you have the graphing calculator, that should be an okay situation. So what I'm going to do now is I'm going to actually let you kind of work on your own here. I'm going to make another video. I want you to do number 2 on your own. It's done exactly like this one is. Okay, it looks very, very similar. And then I'm going to do an additional video over number 3. If you would like to watch it, it will be posted. If you do not want to watch it, you do not have to. Okay, but it's posted on on the Google Classroom, and then you need to finish number 4 as homework. And so really, when we come back on Monday, you should have 2, 3, whether you watch the video or not, and 4 done. That's your homework. You will not have any additional homework for this. You just need to finish 2, 3, and 4. Okay. Keep in mind that 4-6 and 4-7 big ideas are due Sunday night. All right. Just message me if you have questions. Okay.